this video, we're tackling an important problem for coding interviews, longest increasing subsequence from LeetCode. This problem is great for learning about dynamic programming and binary search. Let's break down the problem step by step and understand how the solutions work. So sit back, relax, and let's dive in. So problem statement is given an integer randoms, return the length of the longest strictly increasing subsequence. So first of what is subsequence? Subsequence is an array that can be derived from another array by deleting some or no elements without changing the order of the remaining elements. So for instance, let's take this example. So here, if you have this given array, then this is the subsequence of it. So because we deleted 9 here, this could be a subsequence. So even if we don't delete this could also be a subsequence. And this is also called as subarray because here we did not delete any element in between. So subarray is basically, right, we take all the elements in consideration but in a slicing format of a given list. So if we take this element itself can alone be a subsequence or subarray. Also, if we take this 10, 9, then this itself is a subsequence and subarray. So, but if we take 10, 2, then that would be a subsequence. But 10, 9, 2 would be a subarray. So you got the difference, right? Subarray is something which is contiguous without deleting any element. But subsequence, we can delete the elements, but we have to keep the same order of the element. That means that we can't swap 2 and 5 here. Like we can't take like 10, 5, 2 as a subsequence. Subsequence should be within order. So here subsequence is 10, 2, 5 like that. You understood, right? So similarly in this example also, here if we take this array 0, 1, 2, 3 can be a subsequence, okay? But the subsequence can be a subarray. A subsequence can be a subarray in the cases only if we don't delete any element in between, okay? So let's look into examples. In example 1, we have nums as 10, 9, 2, 5, 3, 7, 101, 18. So here longest increasing subsequence length is 4. So how it is 4? So here 2, 3, 7, 18 is the longest increasing subsequence we have. Okay, so the length is 4. That's why we output 4. In example 2, we have nums is given us 0, 1, 0, 3, 2, 3. So here output is 4 because we have 0, 1, 2, 3 as the longest increasing subsequence and the length is 4. In example 3, this is a different case we have. So here all elements are equal. So as we discussed before, each element can itself be a subsequence or subarray. Okay, so here the longest increasing subsequence is only 1, right? So that's why we output 1. So let's look into constraints here. So first constraint is nums length in the integer range of 1 to 2500. So the moment you see such constraint, what you have to think of is the time complexity which we have to solve this. So here if you take the upper cap of the nums length, we have 2500. So if you do this whole square, what it is 625 into 10 to the power of 4, right? And then if you multiply this again with 2500, so what we have 625 into 25 into 10 to the power of 6. So here 625 into 25 is what? 15625 and 10 power 6. So this is totally what? So we can say, let's take it only 1.5 into all this is for 10 power 4. So which is 10 power 10. So if we consider going like 3 times, we're getting in 10 power 10 range. So which is not feasible, right? Only 10 power 8 operations are possible per second for a given computer. So that case, the max one we go for is only n square to have it accepted solution, okay? So this is the thing which we have to look when they give the length constraint, okay? Next constraint we have is nums of I is the inclusion range of minus 10 power 4 to 10 power 4. So basically they are saying the range of the elements, okay? So each element in the nums lie in the inclusion range of minus 10 power 4, 10 power 4. So on the follow-up they gave is, can you come up with an algorithm that runs in O of n log n time complexity? Yes, we do that, okay? So this is our boilerplate code given wherein we have a method length of lis which takes nums. This nums is what list of integers and it returns the int. So this int is nothing but the length of the longest increasing subsequence, okay? So let's dive into our approaches. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So firstly, let's explore the brute force with recursion. So this would have an exponential time complexity, which of course is not scalable, but this would give an idea how to solve this in naively. So what is the intuition here? So we have to check all possible subsequences and determine if they are increasing. And we recursively compute the length of each subsequence and return the maximum.
Since it examines every subsequence, the time complexity becomes exponential. Okay, so basically here we have to consider every possible subsequence, and we have to say which has the longest length. Okay, so here we're using recursion for this purpose. So basically here, how can we explore the each possible subsequence? So the idea is to include the element in the subsequence and exclude the element in the subsequence. So here we can achieve the longest subsequence either by including or excluding. We don't know that, right? So that's why we consider both paths, and we can check further. Okay, so what is the algorithm here? So for each element, try to include it in the subsequence if it is greater than the last element included. So basically here for the current element, we try to include in a subsequence only if it is greater than the last element. So otherwise there is no point in including the subsequence, right? We want the longest increasing subsequence length. For example, consider this case where we have a 0, 1, 0, 3, 2, 3. So here, what is the possible longest increasing subsequence? 0, 1, 2, 3, right? So here we got this by excluding 0, 3. So likewise, we can exclude some of them and include some of them. So here we included 0, 1, 2, 3. So that's the possibilities we are exploring now. So basically, we have to try exploring either by including a particular element and by excluding the particular element. So that's what we're doing here, okay? Step 2, also explore the possibility of excluding the element from the subsequence. We just saw this, right? We don't know if we can get the longest increasing subsequence by considering this element in our subsequence or by excluding in a subsequence. That's why we try both possibilities. That's the intention here. And then step 3, use a recursion to explore both choices and return the length of the longest increasing subsequence. Okay. And step 4, compare the results of both choices and return the longer subsequence length. So basically here we are exploring both inclusion and exclusion, right? So we can get maximum subsequence from any of this. Okay, so that's why we have to do maximum of these two results and return it. So that's the idea here. So let's look into the code, guys. It would give you more idea. So firstly here we saw, right, this is the main method we have, or the boilerplate code given. So from this boilerplate code, we're just calling a helper method. So this helper method is what? This is to check all the subsequence. So here for this method we define some parameters: nums, index, and previous. So nums is what the given input, and then here this takes the index and previous. So index is what the current element which is being processed, and then previous is what the previous element which was considered before. Okay, so here for this, if index is equals to length of nums, return 0. Why? Because there is no more element left to process, right? So if index is equals to length of nums, that is not a valid index. Index is valid only till length of nums minus 1, right? So that's why we return 0. This is the base case, guys. Okay, in step 1 we exclude the current element. So we discussed right here, we have to exclude and include the current element and check what is the maximum possible length of increasing subsequence. Okay, so that's why here firstly we try excluding. So for excluding, what we do, we just call this helper function again with the nums and index plus 1 and previous. So previous is what, like we using the same previous. That means that here we did not consider the current element as the previous element for the next recursion. So here it is slightly saying that we are excluding the current element. Okay, so we are passing index plus 1 because we process the current index already, right? That's why we pass index plus 1 to say that current index is already processed. Okay, so basically if we pass the same index again, that would be infinite recursion calls, right? So we process this current element, so that's why we do index plus 1, and then we are saying this is not included in our calculation by using the same previous here. Okay, previous is nothing but the previous element. So previous element is processed, same previous element. So that is a way of saying here that current element is excluded. So if you get the more idea by looking into the how do we include it. Okay, so step 2, we include the current element if it is larger than the previous element. So basically we have to include it only in this case. If otherwise there is no purpose of including it, right? We just want the length of the longest increasing subsequence. For that purpose we have to include this current element only if it is greater than the previous element. Okay, that's why we are checking if nums of index is greater than the previous element. So if it is greater than the previous element, we call this recursive function using the index plus 1 comma nums of index. So here you see the difference, right? We were passing previous before, like the same we got in the parameter. So what are the input parameter we got? We are passing here. Okay, now we are passing the nums of index, that is the current index is becoming the previous index for the next recursion call. That means to say that we are including this in our calculation, right? So that's how we include it, and here we are doing 1 plus this one. Why? Because we are including the current index element and then we are checking for the further subsequence. Okay, so that's why to say that current element is included, we do +1 to the result we have. Okay, and then in step 3 we return the maximum of include and exclude. Okay, that's why we do return max of include and exclude. So basically this is the max function we have, which is the maximum value out of these two things. So firstly, how we are calling this, we are sending nums and 0, basically start with the 0th index, and then we are sending the float of -infinity. So this -infinity, what, this would be a larger negative value. So this case would pass, right? So basically the number is even like -1, this would be greater than the previous element. So that's how we pass the -infinity here to get our calculation simpler there. Okay, so what are complexities here? The time complexity is O of 2 power n. Each element can be included or excluded, leading to the exponential combinations. So basically, if you take each element, there are two possible combinations, either to include or to exclude. So 2 into 2 into what? Till the length of the list. So what is the length of the list here? If you take it as n, we have 2 to the power of n possible combinations. That's why it is 2 power n. So space complexity is O of n, because the recursion depth is proportional to the length of the nums, right? So I got the code ready, guys. Let me try running this. So it is accepted for these 3 cases. Let me try submitting this. So you see that time limit is exceeded here. Only 22 out of 55 test cases are passed. This is because this is exponential time complexity and it can't scale for the larger input array. Okay, so that's why we need to optimize it. So let's look into the optimized approaches. So let's look into the recursion stack. I'm just considering index and previous parameters from our helper method we have. So here nums is always a constant one. So that's why I'm just not considering it in our recursion stack representation. So firstly, if you see here, we start with sending 0th index and then sending the previous value as -infinity. And the path for excluding all the indexes all the way from 0 to 4. So basically, if you see here, the previous parameters pass as infinity along this path. Okay, and this is the path for inclusion. So this after this call would return 4. So basically, I'm not considering whole recursion stack, but just a part of it, just to give you an idea of how the recursion stack here involving in computation of subproblems again and again. So if you see here, we make the 6 call for helper of 4 to 10. So here 1 call, 1 call, 1 call, 1 call, 1 call, 1 call. So basically total is 6. And similarly 3 calls for 4, 9. So here we have 3 calls, right? So similarly we have 2 calls for this and 3 calls for helper 3, 10. If you see here, only for this miniature version of the recursion stack, we are making this many repeated calls for the subproblems. That is what making our solution less efficient. So for that purpose, we had to use the dynamic programming in order to not compute the subproblems again and again. Okay, hope you got the idea, because like here we are recomputing the subproblems again and again. That is giving us the time limit exceeded. So we had to move optimally and we had to reuse the results for our subproblems for solving the bigger problems. That's the idea of dynamic programming. So now this is the bottom-up dynamic programming approach, which is the tabulation. What is the intuition here? In this approach, we iteratively fill a DP array where DP of I represents the length of the longest increasing subsequence ending at index I. We update DP of I by comparing the current element with all the previous elements to find if we can extend the subsequence. So you got the idea, right? So let's consider this example, guys. So firstly, what we have here, 0, 1, 0, 3 to 3. This is the given array. So for this, we form a DP array of same length. So this is of length 6, right? So let me just have this DP array and nums here. So this is the index. So firstly, we fill DP array with all ones. And this is the nums 0, 1, 0, 3 to 3. So did you get a doubt that why did I fill DP array with all ones? This is because each element can be a part of a subsequence itself. So basically each element can be a subsequence itself. So that's the idea of filling all DP array with ones. So if you consider the case where all 7s are there, so here we see it output is 1. This is because we discussed, right, each element can be a subsequence itself. So that's why we fill a DP of I with 1. So I stands from 0 to 5 here. Okay. So basically our DP of I should hold the length of longest increasing subsequence ending at that particular index. Okay, so that's why in the worst case as well, we have the 1 as the longest increasing subsequence ending at that particular index. That's why we fill this 1. Okay, hope you got the idea, guys. And next step, what we do, so for each element, we compare it to the previous element and check if we can extend the subsequence from that element. So this is the intuition we discussed here, right? So here we just discussed that, like, we compare the current element with all previous element to find if we can extend the subsequence. So that's what we're doing here. For dp of 0, we don't have any other previous element to compare, so we don't need to compute it again. Now just consider from dp of 1 to 5. Okay, so for dp of 1, so in order to update it, what we check is we compare nums of 1 with nums of 0, because this is our current element, and with current element I'm comparing all the previous elements we have. So here only previous element is nums of 0, which is 0, right? So for filling the dp of 1, what we have to do, we just need to compare max of dp of 1 is equals to max of dp of 1 and dp of 0 plus 1. This is because we have this nums of 1 greater than nums of 0. That means that we can extend. So in case we are extending, we just need to update our dp array. So that's why we're doing this. Okay, so here dp of 1 is what? 1. And dp of 0 is what? 1. Is 1. So max is 2 here. So that's why we fill dp of 1 with 2. Now we are done with dp of 1. So let's go to dp of 2. Same for dp of 2, what we check is we compare this 0 with every other element before it. So 0 is greater than 0? No. So we don't need to update this at this moment. And then is 0 is greater than 1? No. So we don't need to update this one again. So we are at dp of 3. So now we're done till here. Now let's consider dp of 3, guys. So for dp of 3, what we check? So we check if 3 is greater than 0, and that is true. So what we have to do, dp of 3 is equals to this current iteration max of dp of 3 comma dp of 0 plus 1. So now it is max of what? Currently dp of 3 is set to 1 only, and then max of dp of 0 plus 1. dp of 0 is 1. 1 plus 1 is 2. So this is 2. So we just compared 3 with 0 and we got 2. And now we are left with comparison with 1 and 0. So now let's compare 3 with 1. So 3 is greater than 1, obviously. So now what we have to do, we have to update the dp of 3 again. So this is max of dp of 3 and dp of 1 plus 1. So this is max of dp of 3 is what now? 2. And dp of 1 is what? Here if you see, dp of 1 is 2. 2 plus 1 is what? 3. So max of 2 comma 3 is 3. So that's why this would change to 3. So let me just write it properly. 3 now. Okay. Now we're left with comparing with 0. So 3 greater than 0. So now we have to update. So this is max of dp of 3. Okay. And dp of 2 plus 1. Max of 3 comma dp of 2 is what? Here it's 1. 1 plus 1 is what? 2. So max of 3 comma 2 is 3. So that's how we're just left with 3 only here. Okay. So now dp of 3 is 3. So we're now done with dp of 3 as well. Now we are considering dp of 4. So for dp of 4, what we do, we again compare this particular index nums with all the previous elements we have. So 2 is greater than 0, right? So now in that case, we have to update this dp of 4. So now what is dp of 4? dp of 4 will be max of dp of 4 and dp of 0 plus 1. So let me write. So here max of dp of 4 is currently set to 1 and dp of 0 is 1. So 1 plus 1, 2. So it is 2. So now we have dp of 4 is 2. So now we are left with comparing with these three. So now we compare 2 with 1. Obviously 2 is greater than 1. So that's why we need to update our dp of 4 again. Same formula. Max of dp of 4 comma dp of 1 plus 1. So 2. We have dp of 4 is 2 right now. So dp of 1 is what? 2. 2 plus 1, 3. So now we got it 3. So this is 3 now. Okay. And 2 is not greater than 3. So that's why we don't need to update this. This is done. And now we're left with dp of 5 only. So for dp of 5 as well, what is the case here? We compare nums of 5 with every other element before. So here 3 greater than 0. So now we have the same case. We have to update here. dp of 5 is equals to max of dp of 5 comma dp of 0 plus 1. This is what max of 1 comma dp of 0 is 1, 1 plus 1 is 2, so this is 2. So now this is 2, guys. So next thing, what we compare 3 with our 1. So basically 3 greater than 1, so that's why we need to do comparison again in the max here. So dp of 5 and dp of 1 plus 1. So basically it is what max of 2 comma dp of 1 is 2, so 2 plus 1 is 3, this will be 3 now. Okay, so now we have to compare 3 with 0, obviously 3 greater than 0. So now we have to update our dp of 5 again. Dp of 5 is equals to max of dp of 5 and dp of 2 plus 1. So this is equal to max of 3 comma dp of 2 is what 1, 1 plus 1 is what 2, so max of 3 comma 2 is 3, so this remains 3. Now we have to compare with nums of 3. Okay, 3 is not greater than 3, so that's why we skip updation of dp. And then we have to compare 3 with 2. So 3 is greater than 2, obviously we need to update this. So here max of dp of 5 and dp of what index it is, 4, 4 plus 1. So basically max of 3 and dp of 4 is 3, 3 plus 1 is 4, so max of 3 comma 4 is 4. So now this would become 4. So now at the end what we have to return is max of dp. So what is the max of dp here? If you look into the elements, we get the max is 4. Okay, so 4 is the length of the longest increasing subsequence, guys. So that's the intuition. Now let's look into algorithm. So algorithm here is nothing but what we just did in form of steps only. So step 1 means there's a dp array where dp of I holds the length of the longest subsequence ending at index I. Step 2, for each element I, iterate over the previous elements j to check if nums of I is greater than nums of j. And step 3, update dp of I if nums of I can extend the subsequence. So this is the case where we're doing plus 1. This plus 1 is because nums of I can extend the subsequence, it is greater than the previous element j. Okay, so otherwise if it is not greater than the previous element, we don't need to update this. And in step 4, we return the maximum value from the dp array, which holds the length of the longest subsequence. So you got the idea, right? So basically we just discussed here the same thing. So let's look into code. So this is the base case firstly we have. So we're checking if not nums, return 0. That means that if nums is of length 0 or null, we return 0 because we don't have any array to get the longest increasing subsequence. Okay, in step 1, we initialize the dp array with all ones. So basically here this is a short form of initializing the dp array with all ones. So if you're not aware of the syntax, I'll show you a demo here. Firstly, what we have, this is of list of length 1 with 1 value. Okay, so we see only one element. Okay, so what if we multiply with some constant 10? So we get a list of length 10 filled with all ones. So that's what we're doing here. So that means that we're just filling the dp with all ones till the length of nums we have. Okay, makes sense, right? Because dp of I should represent the length of the longest increasing subsequence ending at that index. So we should have this dp array till the length of nums. So that's why we have done this. Okay, and step 2, for each I, check all the previous elements j. So that's what we discussed here, and then we're doing the same thing. So we have the 2 for loops because we have to compare each element with all the previous elements. Okay, and now here we're starting with range 1 because we discussed here, right? For nums of zeros, there is nothing left to compare. So that's why we just keep it 1 and then we continue with index 1. Okay, so here for I in range 1 to length of nums. So this is exclusive now, right? So this would form the index only till 1 to length of nums minus 1. So basically this is the range function, so this would be an exclusive range. So whatever is specified at the end would be exclusive. Okay, and then for j in range I, so basically this would be going from 0 to I minus 1. Okay, so for the given element we're comparing with every other previous elements. That's what the intention is. So we're checking if nums of I is greater than nums of j. In that case we are updating dp of I to be max of dp of I and dp of j plus 1. So this is what we just did here, and this is the same thing we implement in code. So you know, right, we're doing plus 1 because here nums of I can extend the subsequence. So at the end we return the max of dp array. That will give us the length of the longest increasing subsequence. Because we know, right, every index of the DP array holds the length of the longest increasing subsequence ending at that particular index. So if you just take the max out of the DP array, that would give us the maximum length of the longest increasing subsequence. So that's why we do the max of it. Okay. What are complexities here? The time complexity is O of n square, because for every element we compare it to all the previous elements. I got the code ready here. Let me try running this. So this accepts solution for 3 cases. Let me test run this. So guys, this solution is accepted for all the test cases we have, and with 36% of users. Okay. So let's look into approach 3, which is binary search based. So what is the intuition here? In this approach, we use binary search to build a list. List is nothing but a short form of longest increasing subsequence. Okay. This represents the current longest increasing subsequence. The key idea is to replace elements in list when a smaller element is found, ensuring list remains sorted while maintaining the potential for longer increasing subsequences. So guys, before even we get there, I'll tell you the basics of this. So how did we get this approach? So firstly, if we consider the same example as we considered before, 0, 1, 0, 3, 2, 3. So now let's build a LIS from scratch, which is longest increasing subsequence from scratch. So firstly, we start with the empty list. So let's name is list. Okay. So this list, how do we fill it? So firstly, we have a index 0. We have 0. So this is 0. So first, since list is empty, this is still a LIS, because like we have something in list. Each element itself is a LIS, right? So it is length 1. So LIS is of length 1 as of now. Okay. Next we have element 1, so we can append to this one. Basically till here it is increasing, right? So now LIS is equals to 0, 1. Okay, so is of length 2 now, and now we get again 0. So 0 is already here in this LIS, so we can't extend this LIS with 0. So now let's form another LIS. Okay, so because we might get a chance that like we can get a larger subsequence from here, so that's why let's form another LIS only with 0, which is at index 2 here. Okay, so now let's name it LIS1, LIS2. Okay, so here we're done with what till second index. So now we can proceed with third index, which is element 3. So for element 3, we can add it to this LIS 0, 1, 3. So this is of length 3, and we can also add this to LIS2 0, 3. So this is of length 2. Okay, and now we process till index 3. Now we can go to index 4. So for index 4 we have 2. So 2 we can't append to this LIS, and we also can't append to this LIS as well. So now let's start with another set. So basically this LIS is of LIS 3, and before 2 what we have lesser is 0, 1, 2. So we just have elements till 0, 1, 2. So I'm just not reiterating again, so directly put 0, 1, 2. Since we have to consider 2, because who knows, like we might get a longer subsequence starting from these things. Okay, so now we're done till index 4. So now we have element 3, which is at index 5. So element 3 can fit into this. Okay, and it can fit into this, but it can fit into this. So 0, 1, 2, 3. So now we got the longest LIS, which is of length 4. Okay, so basically this is the longest increasing subsequence we have. So you got the idea. So basically here we're considering the list with only increasing elements. So that's the idea, but this is very inefficient, right? We're forming the list each time, so which is not practical. So if you use this solution, this would cause a lot of performance degradation. So we have to think smartly. Now what if we have to achieve this using a single list? Yes, it is possible. How? So let's consider our example again. We have 0, 1, 0, 3 to 3. So let's take a single list LIS. Okay, so this LIS we fill 0, and then we fill 0, 1. I'm just going over indices. Okay, and then again we have 0. So this 0 is not greater than the last element in the list. So in that case, if we find the element which is greater than or equal to the current element, okay, let it be X. Okay, and then if we replace this particular element within the list which is greater than or equal to X, that means that we are able to achieve that within the same list. Okay, so basically here we can replace 0 with 0. Now it is 0, 1. So we are considering 0 as well in this, and then we have this before subsequence, the same length. So we don't lose any length of subsequence here. Okay, so we maintain the subsequence length but have the elements sorted. Okay, and next we have 3. So we can append to this LIS. So 0, 1, 3. and next we have 2. So 2 is less than 3. So in that case, what I discussed, we just need to find the element which is greater than 2 and replace that element with 2. Okay, so basically here 3 is greater than or equal to 2. So here we can replace 3 with 2. So now it becomes 0, 1, 2. So here we don't lose the subsequence length, but we just maintain the subsequence length with the sorted order. That's all. And next we have element 3. So here element 3, it is greater than 2. So we can add to this list. So 0, 1, 2, 3. So you got the idea, right? So basically here we are finding the element which is greater than or equal to x when this x is not greater than the last element in the list. Okay. So that's the idea. We just replace that with the element which is greater than or equal to x. So in that case, we don't lose the subsequence length, but we maintain the subsequence length with the sorted order. Okay. So here also we got a subsequence of length 4. This is the concept, guys. So here for finding the element which is greater than or equal to x, we use the binary search. So that is where we're using the binary search. That's the concept, guys. So let's look into algorithm. Step 1, initialize an empty list to store the increasing subsequence. Step 2, loop through each element x in the input list. If x is greater than all the elements in the list, append x to the list. Otherwise, use binary search to find the first element in list that is greater than or equal to x and replace it with x. This ensures subsequence remains valid while allowing future elements to potentially extend it. So this is something we just discussed here, right? This algorithm is nothing but a sequence of steps what we did. That's all. And step 3, after processing all elements, list will contain the longest increasing subsequence, but not necessarily in its final form. So in step 4, return the length of list, which represents the length of the longest increasing subsequence. So here we just discussed, right? So here the length of the list is what the longest increasing subsequence length. Okay. So let's look into code. So here we're not implementing binary search from scratch, rather we're using the bisect module. From this module, we'll be using the bisect function. So I'll give you the overview of how does that behave. Okay. So here this is the behavior of the bisect function. So basically the element is not present. It returns the index of the first occurrence of the element. So this is with respect to list. So don't worry, we'll see that in action. So if the element is not present in the list, it returns the index where the element can be inserted to keep the list sorted. This element will be greater than or equal to the indices of any existing elements that are less than the specified element and less than the indices of any existing elements that are greater than the specified element. So basically here, this is the same thing what we want, right? So here we want to find the element which is greater than or equal to x if x is less than the last element in the list. Okay. So here, let's see that in action. So we just import the bisect, this is the module we have, and then we have the sorted list. So there as well we have the sorted list, right? So this is 1, 3, 4, 7, 8, 9. And then what we have to search for is element 5. So to keep the element in this list, what index we have to keep it at? In third index, we have to keep it to have the list sorted. Okay. So for this, we're using the bisect function from this bisect module. So we're passing our sorted list and the element. So what does it give us? So let me just execute this. So here, it told it to insert an index 3 to keep it sorted. We also discussed the same thing, right? We thought of keeping at index 3 to have it sorted. 0, 1, 2, 3. So basically at 7, we can keep 5. So if we replace 7 with 5, we still have the list sorted. That's the idea here. So bisect left is actually what we're looking for, this functionality. Okay. So that's why we're using this. And we also have a bisect right. So that has a different behavior. If the element is present, then it would return the index of the last occurrence of the element. Okay. So there is some difference between the bisect left and bisect right. You can just Google it. Okay. So this is our step 1 where we insert the subsequence list. So this is the LIS. Okay. LIS is stand for the short form of longest increasing subsequence. I just kept it as a short form. Okay. So for x in nums, firstly, we check if list is of length 0. Our last element in the list is less than x. That means that if our element is greater than the last element in the list, we can append to the list. So in both cases, we can append, right? So that's why we have an OR case. So here we just do append. In this case, else. Like this is a case where our current element is less than the last element in the list. In that case, we use the bisect module, and in that bisect module, we use the bisect function. Okay. So we just pass the list and x. This would give us the index where we should place our x to keep the array sorted. Okay. So after we get the index, we just replace that index with our current element x. Okay. At the end, we just return the length of list after all the iterations. So basically length of list is what the length of the longest increasing subsequence, right? So that's why we return this. What are the complexes here? The time complexity is O of n log n. The binary search for each element takes O of log n. And since we process each element once, the overall time complex is n log n. So here we're processing all elements. So this is of length n. And each time we perform a binary search, we should take of log n. So combining it is how much? N log n. So this is n log n. And the space complex is O of n because we maintain the list, which in the worst case can store all the elements. So basically, if every element is in an increasing order, then our list would be the same length of our given nums. So that's why it's O of n. So let's take the case where we have 0, 1, 2, 3 as the given list. In this case, our list will hold all the elements because everything here is increasing, right? Each element. So that's why it is a longest increasing subsequence of length 4. In that case, we have the same length as of given array. So that's why we have it O of n. I got the code ready. Let me try running this. This is the accept solution for the 3 cases. Let me try submitting this. So guys, this accept solution for all the test cases and beats almost 100% of users. Cool, right? So congrats guys, we just done the 3 approaches, which is a brute force and a dynamic programming approach and the binary search approach. So hope you remember these approaches and be able to apply these techniques to the other problems as well. And that's your wrap on solving longest increasing subsequence with 3 different approaches. We covered brute force, dynamic programming, and binary search approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.